In 12 days, a massive interstellar object named Tri-I Atlas, weighing 33 billion tons, will pass by the Sun at 80 times the speed of a bullet. It is precisely at this moment that unforeseen events can occur. Its trajectory almost coincides with the plane of the solar system, which is unusual for random comets. This raises a troubling question. Is this object a natural traveler or an artificial machine designed to stop at the Sun and slow down within our solar system? As long as the eyes of the Earth are blinded by the light of the Sun, the only thing we can know is what will appear on the other side. The real threat is that we won't see when it will matter the most. 3 Icarus Atlas ships are racing towards the Sun at nearly 55 kilometers per second, charting a path that defies all odds. Instead of colliding with it at a sharp angle, he passes by the plane of the solar system, tilted only 5 degrees from the ecliptic, an invisible disk on which the planets revolve. For an object from interstellar space, this is a statistical anomaly. Random objects should be scattered across the sky, most of them missing the ecliptic by a significant distance. Nevertheless, the trajectory here almost coincides with planetary orbits, as if it had been pre-planned to merge with the local motion. Orbital simulations conducted by planetary scientists show that only a tiny fraction of interstellar objects should approach in this way. The ecliptic covers a narrow sector of the celestial sphere. For a comet to approach the ecliptic at a distance of 5 degrees is like throwing a dart at a spinning globe and hitting a city street. The last 2 interstellar objects, Oumuamua and Boris, came in at high angles, their paths intersecting the solar system at sharp angles. Atlas describes a retrograde arc moving against the planetary flow, almost horizontally along the disk. This coincidence is not just a curious fact, it alters possible behavior at perihelion. An object approaching along the ecliptic meets the Sun at a shallow angle, maximizing the window for any maneuvers using solar gravity. If a spacecraft designer wanted to take advantage of the Earth's effect to increase rocket power by optimizing its launch for maximum speed near the Sun, this would be the geometry they would choose. However, mere numbers are enough to cause confusion. The object was discovered on July 1, 2025 during the Atlas research in Chile and is only the 3rd confirmed interstellar object. Its entry speed exceeds 200,000 kilometers per hour, confirming that it is not bound to the Sun. The perihelion will occur on October 29, 2025, at a distance of 1.36 astronomical units, slightly closer than Mars's orbit. At this moment, orbital mechanics asserts that it should pass by and disappear forever. However, the strange coincidence of its trajectory with the ecliptic combined with hyperbolic speed leaves a lingering question. Is this a cosmic coincidence or a sign of intent? As the perihelion approaches, the stakes rise. If Atlas is natural, it is a rare but explainable visitor. If not, then the geometry alone suggests a level of planning and intent that goes far beyond chance. At perihelion, the spacecraft Tri-I Atlas will travel at nearly 68 kilometers per second, more than twice the speed of the fastest spacecraft ever launched from Earth. This is the moment when the laws of orbital mechanics provide a unique opportunity. The Oberth effect, first described by Hermann Oberth in 1929, states that burning rocket fuel is much more efficient when performed at high speeds deep within a gravitational well. Simply put, the same impulse from a rocket engine has a much greater effect when the object is moving at maximum speed, especially near a massive body like the Sun. This principle can be reduced to a simple rule. The change in orbital energy when burning fuel is proportional to the object's speed at the moment of burning. If a spacecraft ignites its engines while moving slowly in deep space, it gains only a modest increase in energy. But if you launch the same engines while flying past the Sun at a speed of 68 kilometers per second, the effect will be greatly amplified. A change in speed by 1 kilometer per second at such velocity will lead to a significant change in the object's trajectory. Mathematics is clear. Kinetic energy increases with the square of speed. Therefore, burning fuel at perihelion is like striking with a hammer at full force, not a light touch. For Tri-I Atlas, the theoretical path to capture will require deceleration, that is, reverse burning right at the closest approach. The goal is to reduce enough speed to transition from a hyperbolic trajectory to a closed orbit around the Sun. Calculations show that to transition to a permanent solar orbit at a distance of 1.36 astronomical units, the object will need to lose about 20 kilometers per second at perihelion. This is a huge task. Even for the most efficient chemical or nuclear engines, the amount of fuel required for this will approach the mass of the object itself. Nevertheless, the Oort effect is the only way to make such maneuvering at least remotely possible using known technologies. Natural comets experience outbursts of gas and dust that can slightly alter their trajectories. However, these forces are weak, chaotic, and rarely align with orbital requirements. They can change a comet's speed by a few meters per second, but not by tens of kilometers. Controlled, precisely calculated retro-burning at perihelion would be evident in the data. The resulting trajectory change would be obvious to astronomers tracking the path after solar conjunction. A sharp and significant decrease in output speed, which cannot be explained by natural emissions, would be a bright sign of this. That is why the perihelion window is so important. If Tri-I Atlas tries to slow down, the gravity of the Sun will act as an amplifier, turning a modest push into a significant transformation. The mechanics are simple, and the stakes of energy are enormous. Only signs remain to watch for that nature, or something else has the means and intention to take advantage of them. From mid-October to early November 2025, Tri-I Atlas disappears behind the Sun from Earth's perspective. This is not a coincidence. This is the result of a strict rule in astronomical observations. When an object drops below 30 degrees from the Sun, all major ground telescopes must turn away. Avoiding sunlight is necessary not only to protect sensitive optical systems from blinding light. This is also part of the security protocol embedded in the hardware and software. The period from October 22nd to November 7th means that while 31 Atlas is at perihelion, direct images or spectra cannot be obtained from Earth. Space observatories face the same limitations. The Hubble and James Webb telescopes are set to never aim at areas within 50 to 85 degrees of the Sun, excluding any chance for last-minute observation. Even TESS with its wide-angle cameras is blocked due to solar elongation rules. The Parker Solar Probe and Solar Orbiter, designed for studying the Sun, are directed towards the star and rarely risk deviating from their path to study comets. Their instruments are optimized for studying plasma and magnetic fields, not for weak objects at the edge of the field of view. Orbital Mars probes, in a more favorable position, dared to take pictures as 31 Atlas streaked by in early October, but the object turned out to be 50,000 times dimmer than usual targets, and preliminary images from the ExoMars Trace Gas Orbiter were dismissed by the ESA team as likely noise. No confirmed discoveries have been made. At this moment, the only certainty remains the absence, a prolonged period during which any sudden change, natural or otherwise, can go unnoticed. When the object reappears at dawn in November, astronomers will have to search for evidence of what happened, reconstructing events in the dark. Brightness should serve as an indicator of mass 31 Atlas. However, this assumption is now in doubt. Photometric data calibrated to standard cometary reflectivity estimate the object's mass at about 33 billion tons, making it one of the heaviest natural visitors in recent times. Nevertheless, when the Planetary Dynamics performed calculations after the flyby of Mars on October 3rd, the result was silence. At a distance of only 29 million kilometers, a body of such size should have influenced Mars's orbit, or at least appeared as a small anomaly in the navigation data from the orbiters. Instead, the Mars Reconnaissance Orbiter and ESA's Trace Gas Orbiter detected no measurable deviations. The Deep Space Network tracking logs showed nothing but background noise. This is not just a matter of missed signals. In 2014, the Siding Spring comet, being much closer to Mars, left a detectable trace in the planet's trajectory. Although it was smaller and lighter than Atlas, with a mass estimate many times higher, the effect was completely absent. This discrepancy did not go unnoticed. Astronomical teams double-checked the orbital solutions, searching for any unexplained drifts in Mars's movement or in the timing of spacecraft signals. The answer remains the same. No gravitational influences, no residual effects, no evidence of a massive solid core. Some suggest that the object's mass is simply overestimated and Atlas's brightness may be exaggerated due to dust or an unusually reflective surface. Others point to the possibility of a hollow or highly porous structure, representing a cosmic shell rather than stone. The measured rotation speed, based on periodic changes in brightness, suggests that the body is rotating faster than its size would allow. Currently, the data does not match. A bright, rapidly spinning object with negligible gravity is an equation indicating a hollow shell created by nature or something else. Spectroscopists tracking the object 3 Atlas in mid-September recorded a comet stretching 180,000 kilometers. This cloud of gas and dust significantly surpasses the core itself. The main molecule in these dimensions is hydrogen cyanide, which is released at a rate of 4.5 times 10 to the 25th molecules per second. This is about 2 kilograms of hydrogen cyanide being ejected into space every second. This figure stands out among known comets, but is not without precedent. The enormous size of the coma and stable output of cyanide suggest active gas release caused by the sun-warming ancient ice. As Atlas approaches the inner part of the solar system, jets of steam and dust burst outward, forming an asymmetric shell subject to radiation pressure and solar wind, signaling movement and instability. However, the chemical composition is not just a curiosity. It serves as a basis for how a natural comet should look before perihelion. The presence of cyanogen alongside traces of water and carbon monoxide anchors Atlas in the familiar realm of solar system comets. Spectral signatures correspond to those recorded from previous interstellar visitors, although the ratios and intensities hint at a unique formation history. Currently, the behavior of the comet supports a natural explanation: a porous body rich in volatile substances, losing mass as it approaches the sun. This basic information, gathered before the critical solar encounter, will serve as a benchmark for assessing any changes after perihelion. If the chemical composition changes or the coma fragments unexpectedly, these deviations will stand out against the meticulous records of spectroscopists from September. The hollow shell racing towards the sun is not just a physical mystery. It is a scenario with verifiable consequences. Imagine a structure created not to endure, but to arrange. At perihelion, when sunlight and gravity reach their peak, a fragile body may naturally fragment, scattering debris in random directions. However, there is another possibility that scientists like Avibe persistently keep on the agenda: intentional deployment. If the Object 3 Joe Atlas is artificially created, perihelion provides a unique moment for action. Instead of chaotic destruction, the shell can release smaller units, probes, or sensors, each with its own trajectory, like dandelion seeds catching a gust of wind. In this case, the evidence will be obvious. After perihelion, astronomers will search for distinct, non-random tracks emanating from the original path. Some fragments accelerate or move away from the sun, rather than simply drifting in space. A pattern in the field of debris, straight lines, sharp changes in speed or clusters, moving as if under control, would stand out against the backdrop of natural chaos. The Low Project Galileo is preparing for exactly such a test. Their checklist is clear: track every outgoing fragment, measure speeds, compare with models of natural comet disintegration. If the data shows randomness, the scenario with controlled objects loses meaning. But if order is found in the sky, it will have profound consequences. The days after perihelion will determine which story the collected evidence supports. The ExoMar orbital device, designed to study the Martian surface, was used when 3 objects, named Ice Atlas, flew past Mars in early October. The team working with tools disconnected the high-resolution camera from the planet and directed it into the darkness of space, making a series of 5-second exposures, each stretched to the technical limit. The target was almost 50,000 times dimmer than anything the orbital device was designed for. Raw footage showed only the scattering of digital noise. In most cases, the presumed comet was indistinguishable against the noise. Processing systems tuned to clear Martian landscapes struggled to extract any reliable signals. Analysts from the European Space Agency marked preliminary images as likely noise, lacking the confidence to even assert a weak detection. The problem was not only the dullness of the objects. Mars orbiters transmit data to Earth within narrow timeframes, competing with planetary science priorities and bottlenecks in data transmission. Each batch of images undergoes multi-layer calibration, compression, and verification before entering the public archives. Since the object was so close to the Sun from Earth's perspective, it was impossible to match these ambiguous frames with ground observations. By the time any processed data becomes available to the public, scheduled for the end of November, a week will have passed since perihelion. During this time, any sharp change in the trajectory or structure of the Atlas could have gone unnoticed. For analysts, each uncertain pixel was a reminder. The most critical moment could be hidden in the noise, and the only clues might come too late to be captured in real time. An object caught by the sun from interstellar space would rewrite the rules of planetary science, representing the first permanent sample of exoplanetary material for researchers to study for generations. For defense planners, this scenario was less academic. Internal documents circulating in NASA and the U.S. Air Force during the time when information was unavailable described models for unforeseen circumstances. If the controlled object used a perihelion maneuver to reduce speed, observation protocols would be intensified. No agency has released public recommendations or threat assessments, but the existence of these drafts, even in edited form, signals a change in the approach to modeling such events. A single headline about a capture or deployment of a probe could evoke a wave of emotions far exceeding the interests of the scientific community. However, despite all the assumptions, the main criterion remains the facts. Observers need a clear checklist to evaluate unusual claims. First, one must pay attention to the sharp change in the speed of the object, a sudden fall visible in the astrometric remnants that cannot be explained by gas ejections. Then, it is worth looking for organized debris. These can be separate trajectories or fragments moving in non-random directions rather than a chaotic spread from natural destruction. Compare this to recordings of atmospheric anomalies, especially reports of events similar to unidentified flying objects synchronized with perihelion. Observations to note include publicly available optical and radar data from Earth and space, polarization studies, and citizen science campaigns on occultation in the Southern Hemisphere. NASA, ESA, CNSA, and the Galileo Project archive channels will release restoration images, trajectory solutions, and raw sensor data in November and December. The rule is the possibility of refutation. If the path of movement shows no sharp changes, if fragments drift randomly, if correlated anomalies do not appear, history returns to nature. The test is not in what is possible, but in what the data confirms. On October 29, 2025, Comet 3I Atlas will reach perihelion at a distance of 1.36 astronomical units from the Sun, confirmed by both Atlas observation records and NASA trajectory data. His approach to the ecliptic at an angle of 5 degrees is statistically rare for interstellar objects, which is also confirmed by orbital models. Although photometric data estimates the mass at 33 billion tons, the flyby past Mars on October 3rd showed no detectable gravitational effect, as recorded in the navigation logs of ESA and NASA. Gaps in images during the eclipse at the upper conjunction are explained by published graphs of telescope operations, leaving a critical window for observations unrecorded. At this point, no secret information about the potential capture of the object or its artificial origin has been published. Regardless of whether the 3I Atlas is a porous comet or something artificially created, only the data on debris patterns and speed changes after perihelion, expected in the November datasets, can provide answers. At this point, the facts highlight both the limitations of current observations and the unusual nature of the 3I Atlas. Its next step remains a matter of recording, not assumptions.